Okay, so now we're going to talk about what molecules look like and what the structures look like. So we're actually going to be doing a little bit of art. I'm not particularly artistic, so bear with me. So we're talking about how the electrons arrange themselves around an atom in bonds. Remember, bonds are the glue that hold them together, so now we're talking about how they line themselves up. So we're going to create these things called Lewis structures, and basically they're a picture that show how the electrons are arranged in bonds and not when they're forming compounds. So you need to be able to determine the number of valence electrons for an atom. Remember the easy way when we did this in the electron configuration chapter. It's the number of electrons in the highest energy level, but you can get that straight off the periodic table. And here's the number one rule. Put a little star next to this. All atoms are going to form bonds in a way so that they have 8 electrons around them. Remember, that's a full shell like the noble gases, and they want to be low energy like noble gases, very stable like noble gases. And so those 8 electrons around them are either bonded, remember that's the glue that holds them together, or what's referred to as lone pairs, and we'll talk about that in a minute. And that's referred to as the octet rule. There is one exception that you guys need to know about for now. Hydrogen is just, it's so small an atom, it only follows what they call the Duret rule. It only gets 2 electrons, never 8. Okay, so 2 big ideas when we're drawing these pictures. First of all, it's a picture, and it does have some rules that go along with it, and it works for the majority of the things. We are generally talking about nonpolar molecules, or molecules with nonpolar covalent bonds and ones with polar covalent bonds, not ionic. We really don't do it with ionic. And it's based on the valence electrons and a few other rules. And these sketches are really actually kind of important because we use them to help predict some of the basic chemical and physical behavior of the molecules. It helps explain why some things do some things, certain things, and other ones don't. This is what a Lewis structure looks like. Okay, the lines are referred to as a bonded pair. Remember, that's the glue that holds the atom together, and it can be nonpolar covalent or polar covalent, probably not ionic. So those are the electrons that hold the Br and the N together. These ones on the outside, the dots, those are called lone pairs. And they aren't shared with anybody. They belong only to the atom on which they are drawn. Okay, so this nitrogen, those 2 electrons belong to it, whereas it's got bonded electrons that it's sharing either equally or unequally with the bromines. So we're going to start simple. I'll show you how to do this. So you want to count the total number of valence electrons in the molecule. Well, fluorine is in column 17. That means it has 7 valence electrons, and there are 2 of them. So here's where we're going to use those subscripts. We're going to have 7 times 2 means 14 valence electrons. Then you're going to arrange the atoms in the most likely arrangement. That means you're going to draw a picture, and you're going to put them side by side, top and bottom. Doesn't really matter. Okay, I'm probably going to go side to side because I read left to right, I write left to right. That's what I'm going to do. Okay, then you're going to put the electrons in as dots between the 2 atoms. This is the bond, the glue that holds them together. Okay, so you have F and you have F. And I'm going to make them share 2 electrons. That's the rule. Oops, let me erase the ink here. So the rule is the electrons that they share is 2 electrons being shared equally in this case because it's a nonpolar covalent bond. They're being shared between the atoms, and most often it's represented as a line. So one line represents 2 electrons shared between the atoms. Okay. Then you're going to put electrons around the outside edges of each atom. So that would be those lone pair things. And the way you do it is everything wants to have 8. And I'm drawing my dots deliberately on here. So what I have, and I'm going to erase that bottom picture right here. What you do is you put a bond in the middle. That represents 2 electrons shared. Then you have 1, 2, 3, 4, 5, 6 on this fluorine. So this fluorine has 3 lone pairs to itself, or 6 electrons to itself. This one has 3 lone pairs, or 6 electrons to itself, and each one of them, they're both sharing 2 electrons. So from the perspective of this guy, he's like, yeah, I got 6 of my own, and I've got 2 more, I've got 8. And then from the perspective of this one, 6 of his own, and sharing 2. So he has 8. So we're following the octet rule. All right, the other rule is it has to add up. According to the picture, it has to add up to the total number of electrons that I have available. If you remember, I had 14 valence electrons to work with. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This is a good octet or Lewis structure. So you want to double check. This is what it looks like. That all atoms have 8 pairs around them, or 8 electrons, 4 pairs, 2, 4, 6, 8, 2, 4, 6, 8. And you want to double check to make sure that it adds up to 14. In this case it does. It's a good Lewis structure. Keep in mind, when you're doing hydrogen, only gets 2. It never gets dots. It only shares. It's 1 bond only for hydrogen. Okay? So let's do water. So first thing we're going to do is H2O. We're going to figure out the total number of valence electrons. Hydrogen is in column 1, so it has 1 valence electron. Multiply by 2 because of the coefficient. Oxygen's in column 16. It has 6. So you have a total of 8 to work with. Now, one of the other things that makes this a little bit easier is if you put the atom that's all by itself in the middle, and then you put the other atoms around it, top, bottom, left, right. Okay? So that oxygen's in the middle because there's only one of them. It is going to share electrons with the hydrogen atoms, and right now they're sharing, this hydrogen and this oxygen are sharing 2 electrons. This hydrogen and that oxygen are sharing 2 electrons. And remember, hydrogen only gets a line. So the hydrogens right now are done. They don't need anything else. Then you're going to fulfill the octet rule. And oxygen right now is sharing 2 with this hydrogen and 2 with that hydrogen. So it's sharing 4 electrons, which means it needs 4 more of its own. And it's got 4 in lone pairs. So it's good. And then 1, 2, 3, 4, 5, 6, 7, 8 adds up to 8, and the oxygen has 8 around it. Hydrogen doesn't count, doesn't need 8. And that's a good Lewis structure. Okay, so how do we get to this point? So you count the total number of valence electrons for NBr3. N has 5, Br has 7, but there's 3 atoms. You got 26. Okay. Then you want to arrange the atoms in the most logical way and connect with bonds. And again, hydrogen is only on the outside, but everything else that's a single atom usually goes in the middle. So in this case, I'm going to put N in the middle, Br, Br, and Br. You could do any top, bottom, left, right, doesn't really matter. Then you're going to connect them with a bond between them. And right now that nitrogen is sharing 2 electrons with the bottom bromine, 2 electrons with the left bromine, and 2 electrons with the right bromine. And so it is got 6 electrons around it. It needs 2 more to make it have an octet. And then each one of those bromines is sharing 2, so they need 6 more to have an octet. Okay, and then it has to add up to 26. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Done. Okay, so go ahead, take a minute, and practice HF and CH4, or CF4. So this one, you got 1 plus 7 valence electrons. CF4, you've got 4 plus 7 times 4 is 32. You might notice you have even numbers all the time. And the reason you have even numbers is because everything goes in pairs. If you have an odd number of electrons, something's wrong. Okay, I won't give you to draw those. So for this one, H, F, make them share. They have to have a bond. The fluorine is the only one that needs to have 8 around it. So right now the fluorine has 8, 2, 4, 6, 8. Total of 8, done. CF4, C in the middle. F's on the outside, and I just automatically make them share. So right now the carbon is sharing 2 electrons with every one of the outside fluorines. So the carbon is done. Carbon doesn't very often get dots. And then for the fluorines, each of the fluorines right now has 2, so they need 6 more on each of them. And if you add this up, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, done. So go ahead, take a minute, pause the movie. I'm going to put the correct answers up here and see if you guys can come up with them. Okay, so let's do the electrons first. N is 5, 3 times 7 means total of 26. Si is 4, plus each of the hydrogens is 1, times 4 is 8. Hydrogen is 1, times 2, plus sulfur is 6, is 8. And the Cl is 7, plus 6 times 4. And then this negative 1 means you add an electron. That's really important, otherwise you're going to end up with an odd number. So 24, 32. Okay, so for the NCl3, N's in the middle, Cl's on the 3 of the 4 sides, N needs 2 in the middle. People have a tendency to forget that. Don't forget the guy in the middle. And then each of the Cl's on the outside needs 6. Done. SiH4, Si in the middle, H on the outside. Si has 8 around it, and the hydrogens are done. Remember, hydrogen only gets a single line. H2S, you got H, S, H, looks like this. And then the ClO4 1 minus, that one's a little tricky. Like I said, don't forget, if it's a negative charge, you would add an electron. If it was a positive charge, you would actually subtract. So Cl in the middle, O's on the outside. And because it has a charge, technically you need to put it inside brackets and give it a negative 1 charge on the outside. Okay, so now go ahead and let's try this one. Okay, so at this point you're probably pretty good at it. It's not that hard to do. So for sulfur dioxide, if you add up sulfur dioxide, you have 6 plus 6 times 2 is a total of 18. S in the middle, O's on the outside. Give everything 8. Now if you add this up though, so everything's got 8, right? This oxygen has 8, the sulfur has 8, the oxygen has 8. If you do that, you might notice that that adds up to 20 electrons, and I only had 18 to work with. Okay, this is a situation where you run into some problems. Okay, so you want to follow the octet rule, but what you're going to have to do is take that Lewis structure and you're going to have to change it a little bit. Because I've drawn 20, I'm not allowed to draw 20. But everything has to have 8. So what I recommend you do is you draw the structure following the octet rule. If you count and you have too many drawn, here's where it's a great idea to use pencil. Erase 2 on the middle atom and then pick an outside atom. I'll pick that one. So I've erased 4. I've lost 4. But then what I'm going to do is I'm going to make them share 2. So it's a net loss of 2. I erased 4, 2 on the middle, and 2 on an outside atom. And instead of keeping those as lone pairs to themselves, I made them share an extra pair. This is called a double bond. And in this case, the oxygen is sharing 4 electrons with the sulfur, and it has 4 of its own. This sulfur is sharing 2 with the oxygen over there and 4 with the oxygen here, so sharing 6 and 2 of its own, and the oxygen on the end didn't change at all. And now if you add it up, it adds up to 18. So when do you use double bonds? Draw the Lewis structure with single bonds and follow the octet rule first. That's what we just did. If you have done that and you've drawn too many dots, you've exceeded the amount you had to work with, you will need to decrease the amount you've drawn but still obey the octet rule. And the way you do that is you remove 2 dots from each atom on either side of the bond. So from the center and the outside, dropping the total by 4. Then you add a double bond back, which means you're adding back 2 electrons, but these guys are shared between the 2 atoms that you took the 4 from. And so they've lost 2 of their own, and now they're sharing 2. And so what that does is it drops your total down by 2. And repeat as needed. However, you will never have more than a triple bond. There's no such thing. Okay, triple bond is as many as you can do. You can't do quadruple bonds or anything else. And hydrogen always has a single bond and no dots. That's where the big stroke comes in. So go ahead, see if you can do these guys. Carbon is 4. 6 times 2 for oxygen is 16. 5 times 2 here. So I'm going to draw it with single bonds. Give everything 8. I'm going to draw this with single bonds. Give everything 8. And then I'm going to count and go, okay, let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18. Oops, I erased one of my bonds. So what I need to do is put the bond back, erase 2 on the center atom and 2 on the outside atom, and make them share. So if I count that, 2, 4, 6, 8, 10, 12, 14, 16, 18. Still too many. And so here's where you have a choice. You can erase, you have to erase 2 on the center atom. And you could erase 2 from this atom over here, or 2 from that atom. I'm going to do it here. And I'm going to make them share a double bond. So right now the carbon has no lone pairs of its own. Carbon doesn't very often get dots. The oxygen has 2 lone pairs of its own, and it's sharing 4 in bonds. So that one's done. You could also have done this. And that's something called resonance, and we'll talk about that in the next movie. But the idea is it has to add up to 16, and everything has to have 8 except hydrogen. So now if I'm looking at the nitrogens, I see 2, 4, 6, 8, 10, 12, 14, and I'm only allowed to have 10. So I'm going to erase 2 here and 2 here and make them share, because I only have 10 to work with. 2, 4, 6, 8, 10, 12. Still have too many, so I'm going to erase 1 more pair on each atom, knocking it down by 4, and making them share 2 more. So that's called a triple bond. Okay, so go ahead and try these guys. I'll put the correct answers up there. So for CO3 2-, it's 4 plus 6 times 3 plus 2 is 24. C in the middle ends up with a double bond to one of the oxygens, and it doesn't matter which one. Again, that's something called resonance. And there you go. That's the way it works for that one. SCN1-, you got 6 plus 4 plus 5 plus 1 is a total of 16 again. S and C and N. C's in the middle. It's usually in the order it's written. And when you're done, you could end up with that, or, oops, that, or that. Any one of these options is an acceptable Lewis structure, because they all add up to 16, and every single one of them, each of the atoms has 8.